All right. So we're going to do simulations, and we're going to need a little bit of brain power when doing this because we've really got to pretend. And um, simulations are done when it is unsafe, unethical, or just impossible to actually try to do something in a real world scheme. So we're also going to look at something different called a random number table this time around. And when we do all this, the difficulty is realizing that I think the biggest difficulty is realizing how simple this is. But then the other difficulty is then realizing how this is actually done by people. And we sit here and we're like, this seems so simple. Who would do this? And yet, there is a book of random number tables that has been exalted by engineers and statisticians for the past 65 years. Um, there's a whole corporation dedicated to statistical sampling and and simulating things so that people don't get injured, and so that we can take data and just run with ideas. So this is a real thing. It just feels kind of weird. I have to admit that. So a basketball player makes 80% of her free throw attempts. What's the likelihood that she makes at least two of her next free throws? Well, if you were to guess right now, you would guess, well, it's likely to get the first, and so it's also likely to get the second. So you would probably guess it's likely. So we're going to use the three-digit number over here, and we're going to actually run a simulation. And then we'll talk about what simulations are in full. So here we go. Using the three-digit number, because 80%, now the numbers that we can use are 0 through 9. And so we want all the numbers, so we want 8 of them to make 80%, because this is 10 numbers here. 10 numbers. And since it's 10 numbers, we want to take 8 of those 10. So let's say that any number 1 through 8 is a success, and any number 0 or 9 is a failure. So we're going to look for her making at least 2 free throws. So that means we're looking for, so let's just show you. 8, 3, 8, since all 3 of those numbers are between 1 and 8, this is 3 successes. Over here, we've got 6, 1, 7. That's 3 successes. Over here, 2, 8, 2, we've got 3 successes. 3, 4, 1, that's 3 successes. 7, 8, 5, that's 3 successes. 7, 4, 7, she's made all 3. 3, 3, 2, she's making all 3 again. 2, 7, 9, oh, she only gets 2 on that one. 0, 8, 2, she gets 2 on that one. 3, 7, 6, that's 3 of them. 9, 3, 7, she makes 2 of them. Here, 308, she makes 2. 800, she only makes 1 of them. Right here, 994, she only made 1. 689, she makes 2 of them. 198, she makes 2 of them. 025, she makes 2. 853, she makes all 3. 591, she makes 2 of them. 813, she makes 2 of them. 672, that's 3 of them. Whoops. 672, she makes 3. 289, she makes 2. 518, she makes 3. 649, she makes 2. 540, she makes 2. 865, she makes all 3. 631, she makes all 3. 227, she makes all 3. 004, she only makes 1. And 840, she makes 2. So if we look here, we did 1, 2, 3, 4, 5. 6, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. So we've got 6 times 5. We've got 30 outcomes. And out of them, so the probability of at least 2 free throws. Oh, well, that's okay. Let's just look at the problems here. Because at least 2 free throws is also down there. So we'll actually solve it then. Exactly 2 free throws. So exactly 2. Let me see if I can still find the highlighter feature here. Mark up. Freehand highlighter. Does this do it? Yeah. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I've got 12 out of 30. 12 out of 30. Come over here. 12 divided by 30. That gives us 40%. 40% for exactly 2 free throws. At most 1 free throw. Let's see what that is. At most 1. At most 1 would be 1 or none. So 1, 2, 3, and there's no nones, so this will be 3 out of 30, which is 10%. Mr. Manchester, how did you know that? Because 3 divided by 30 is 0.1 times 100 is 10%. At least 2 free throws. At least 2 means that we want 2 or more. And so let's look at this. Go so 1. Oh, that's the text one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. Now, what we could have done instead of doing all that was we could have just gone 30 minus 3, because at least 2 free throws is the complement of at most 1 free throw. But I forgot about that until I started counting. But nonetheless, we have 27 over 30. 27 divided by 3 is 9, so this is 90%. And remember, we said it was likely. We said that it should seem likely, and indeed it wasn't likely. And then at least 2 free throws in a row. Now this is going to get interesting. So over here, I'm going to see if I can do this, because this is pretty... There we go. I can. Come on. Delete those. Delete those. And delete this. Good. All right. 2 in a row. Let's find 2 in a row. So this first one has 2 in a row. The second one has 2 in a row. This third one has 2 in a row. This has 2 in a row. 2 in a row. 2 in a row. 2 in a row, 2 in a row, the first 2, 2 in a row, the last 2, 2 in a row. Yeah, every time you have a 3, that's a 2 in a row, by the way. So I'm just going to cross those all on out here. This one has 2 in a row on a back end. This one does not have 2 in a row. This one does not have 2 in a row. This one does not have 2 in a row. This one does not have 2 in a row. This one has 2 in a row on the front end. This one does not have 2 in a row. This one has 2 in a row on the back end. This one does not have 2 in a row. This one has 2 in a row on the front. This has 2 in a row on the front. This one has 2 in a row on the front. This one has 2 in a row on the front. So if I look here, at least 2 free throws in a row. So if I count the ones that are not free throws in a row, that'll be easier. 1, 2, 3, 4, 5, 6. We have 6 that are not free throws in a row. So that's 24 out of 30, which would give us 80%. So 80% of the time, we're predicting that she's going to get 2 free throws in a row. All right. So let us play. Okay. A simulation is an experiment that is designed to reproduce the conditions of a situation or process. Simulations allow you to study situations that are impractical to create in real life. For instance, a dog has 3 puppies. The sex of each puppy is equally likely. To simulate 2 outcomes that are equally likely, we can flip a coin. We're going to say that if the puppy is male, the coin is heads. If puppy is female, the coin is tails. Now, I'm going to go to random.org. Random.org is a website that'll give you a bunch of random numbers. But it also does coin flipping. And so we're going to look at this. We want 20 trials, so we're going to flip 20. Let's go with, keep it simple. We'll flip 20 pennies, and then we'll copy down the results. Oh, I don't need 20 pennies. I need 60 pennies. I'm sorry. I need 60 pennies because we're having 3 puppies. So, not a big deal. Let's just... Because, see, flipping 60 coins is going to be annoying. In class, I'll have a way for us to do that. But here we go. Copying this table down, we go heads, tails, tails. That's the first 3. Tails, tails, heads. That's the second 3. Heads, tails, tails. Heads, tails, heads. Heads, tails, 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 heads, heads. I'm on row 3 right there. Starting here, I get tails, tails, tails. Moving over to here, I get heads, tails, tails. Next row, I get heads, heads, heads. Then I have heads, tails, tails. Then I have tails, heads, heads. Then I have 3 heads in a row, heads, heads, heads. Whoops, wrong one. Want to be over here on this side. Whoops. Then I go here with tails, heads, tails, heads, tails, heads, tails, heads, tails, 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 tails. Oops, I just wrote down heads. That was weird. Then we go last rows, heads, tails, heads, tails, heads, tails, and tails, tails, heads, and heads, tails, heads. Okay, so there's our table. Now from that, what's the probability that all 3 puppies are males? So 3 puppies being male, that would be 3 heads. We have 3 heads here, and we have 3 heads here. So that is 2 out of the 20. So our probability that we're running is 10%. Another example, you have a 60% chance of winning a board game and a 20% chance of winning a card game. Design and use a simulation involving 50 randomly generated numbers to estimate the probability of winning both games. Well, in class, I was just going to ask people for the last 4 digits of their phone number, and we'd go with that as random numbers. I might still do that. I'm not 100% sure. Definition of randomness is, that's actually, believe it or not true randomness. So part of me kind of doesn't like that idea. So I'm going to instead use, for us at home, I'm going to use a random number table that I generate using Microsoft Excel. And we're just going to use these numbers. And we're going to say that winning a board game is the digits 1 through 6. Winning the card game is the digits 1 and 2. So let me do this. And then, whoops. I'll do this, and I'll show you guys at home how this works, because if you're absent today, this gets really kind of confusing unless you watch this. So our number table says 5 and 8, 3 and 4, 1 and 0, that's a 4 right there. 7 and 2, 3 and 1, 3, 5, 9, 2, 2, 1, 4, 4, 1, 0. That second 4 seems to be a hard thing to do. We have 8, 9, 8, 3. I'll explain what we're going to do with these numbers in a moment. 4, 3, 1, 1, 7, 4, 4, 3. Dab nabbit, my 4s do not come out right. 4, 3, 8, 2, 6, 5, 5, 5, 6, 1, 5, 1, 1, 2, 0, 9, 9, 4, 9, sorry, 8, 9, 2, 4, 0, 3. There. I do not understand why. All right, 6, 1, 8, 5, 3, 7. Almost there. 2, 3, 1, 7, 6, 3, 0, 7, 9, 4. Finally, a 4 that wrote well. 4, 2, 7, 1, 6, 9, 7, 2, 0, 9, 2, 5, 5, 2, 2, 0, 3, 1, 2, 2, 2, 8, 8, 1, 3, 1, 3, 6, 0, 3. There we go. So we're going to find out, using our table, what's the probability of winning both games. So we want to see a 1. We want things like 11 or 12 or 21, 22, 31, 32, 41, 42, 51, 52, and 61, 62. So we look through here. We know the first one can't win, second one can't win, third one can't win. This one could, nope, because the front number doesn't work. Here we go. There's our first winner, 31. Our second winner right here at 21. Looking through here, third winner at 11. Next, 61's a winner. 51's a winner. 12's a winner. 61 is a winner. And then 42 is a winner. 71 is not. 72 is not. 52 is a winner. 31 is a winner. 22 is a winner. 31 is a winner. So we've got all of our winners. All right, so now we just need to count them all up. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 12 winners out of the 50 numbers, 50 trials that we ran in our simulation. So if I pull up a calculator then, 12 divided by 50 gives us 0.24 times 100 is 24%. So we're expecting a win 24% of the time. I will tell you, running the simulation, this is actually a higher percent chance than theoretical. I find that interesting. In the last one, it's actually, I think it's a lower percent chance than theoretical. So I find that interesting too. I find it just interesting to run the simulations knowing that theoretically we have answers to these, and our answers are not quite the same. So this time around, I made the tables already pre-made. 4 multiple choice questions on a quiz, each have 5 answer choices. You randomly guess the answer to each question. Design and use a simulation to find the experimental probability that you answer all the questions correctly. So we have 4 possible questions. We have 5 possible answers. Let's make the numbers 1 through 5 correct. Let's make the numbers 0 and then 6 through 9 as incorrect. So if the numbers are all 1 through 5, we get all the answers correct. So let's go through here and see which ones have all 1 through 5. So this one doesn't, nope, 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 nope. There we go. No, because that's got the 0 in it. Nope, 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 nope. Wow, a lot of these things have no's. Well, oh, no. Well then, here's one and here's one. There we go. So in all that, I see 3 out of, I think we said there were 50. So 3 out of 50. And so that means if we come over here, 3 divided by 50, that's 6%. So our experimental probability that you answer all the questions correctly is 6%. Okay, cool. Like I said, I feel like there should be something more to this, and there isn't. You're just looking at the numbers. So for instance, over here, you select a marble from a bag of chips. You have a 20% chance of choosing green, 90% chance of choosing red. Estimate the probability that you choose green and red. So the numbers 1 and 2 will mean that you choose a green marble. So 0 and then 3 through 9 mean that you do not choose a green. That's for the first number. So we're going to be looking for numbers that start with 1 and 2. Then numbers 90% chance, let's go through 1 through 9. And if it has a 0, it means you did not choose red chip. So we're basically looking for anything except for 10 and 20. So anything in the teens and 20s except for 10 and 20. So 15 works, 12 will work, 26 will work, 24 will work, 25 will work, 20 doesn't work, 14 will work. I forgot my tens. Okay, that looks to be all of them. So we got 1, 2, 3, 4, 5, 6. We have 6 out of 50. And so our experimental probability, 6 divided by 50, is 12%. Now, if you were to run the simulation with completely different sets of numbers, if I decided to put in new sets of numbers, you'd get different results. But then what you could do is you could stop and look at your simulations and start going, okay, well, this one gets to here, this one gets there. Do we have any simulations that are anomalies? We can start actually like narrowing down with our simulations. We'd get closer and closer to the actual theoretical probability. So, yeah, because that's lower than theoretical probability, but I'm okay with that. And the other one, I think is higher, but yeah, it's because. Yeah, anyway, you probably don't care too much, but I mean, you have a 20% chance on each one for answering the question. So, yeah. So, you have a very, very, very small percent chance of guessing all 3 of the question or all 4 of the questions right. Oh, I did 5 of them, not 4 of them. Should be 0.2 times 0.2 times 0.2 times 0.2 times 100. So you'd have 0.16% chance of actually getting all of them right, if I'm remembering how to do some of the stuff correctly. So anyway, you randomly go, yeah. All right. So anyway, that's all I have for you. Hopefully this helps you see what a simulation is and how we can run them on paper without hurting people. Thanks. Bye.